Welcome to the session on variable acceleration, review exercises. The objectives for this session are to review previous topics through exercises, namely, explore examples of differentiating functions with two or more terms, find the stationary points of a polynomial, find f of x given f dash of x and a point on the curve, and find the area bounded by curves and straight lines. Pause the video and have a go at these review exercises. When you are ready to view the solutions, press play. Let's begin by looking at differentiation. Powers of x and quadratics. Recall that for all real values of n and for a constant a, if y equals ax to the power n, then dy dx equals an times x to the power n minus 1. If we're differentiating multiple terms, for example, if y equals f of x plus or minus g of x, then dy dx equals f dash of x plus or minus g dash of x, where f dash of x and g dash of x are the differentiated expressions of f of x and g of x, respectively. Let's now take a look at review exercise 1. We are required to find the derivatives of the expressions given on your screen. So let's solve part A first. If y equals 2x cubed plus 9x, we have that dy dx equals 2 times 3 times x to the power 3 minus 1 plus 9. And therefore tidying up gives us that dy dx equals 6x squared plus 9. And now for part B. If we have y equals x to the power 4 plus x cubed minus 2 root x, we can rewrite 2 root x as 2x to the power half as shown. So, use the second form of the equation in our calculations, as this is easier to work with when differentiating. So now let's differentiate. We have that dy dx equals 4x to the 4 minus 1 plus 3x to the 3 minus 1 minus 2 times a half times x to the half minus 1. And tidying up gives us 4x cubed plus 3x squared minus x to the minus half. Let's now take a look at integration. The rule for integrating kx to the power n is that if f dash of x equals kx to the power n, then f of x equals k over n plus 1 times x to the power n plus 1 plus c, where c is a constant and n does not equal minus 1. When integrating polynomials, apply the rule for integration separately to each term. For definite integrals, if f dash of x is the derivative of f of x for all x in the interval ab, then the definite integral is defined as integral from a to b f dash of x dx equals, and in square brackets, f of x between limits a and b, which equals f of b minus f of a. Let's also now look at the steps for integrating definite integrals. First, write the definite integral statement within its limits as shown. Next, integrate and write the integral in square brackets as shown. And finally, evaluate the integral by working out f of b minus f of a. In order to tackle review exercise 2, we require some more background information. So let's remind ourselves of the nature of stationary points and in particular the steps for finding stationary points. First, find dy dx of the function and put it equal to 0. Next, solve for x. And finally, substitute x in the original equation to find y. Let's now have a go at review exercise 2. We are required to find the coordinates of the stationary points on the curve with equation y equals 2x cubed minus 15x squared plus 36x plus 2. So let's remind ourselves of the rules of differentiation. If y equals ax to the power n, then dy dx equals an times x to the power n minus 1. Let's now use this to tackle review exercise 2. So differentiating y gives us dy dx equals 6x squared minus 30x plus 36. And factorising gives us that dy dx equals 6 times x minus 2 times x minus 3. If we put dy dx equal to 0, we have either x equals 2 or x equals 3. Now when x equals 2, y equals 30. And when x equals 3, y equals 29. Therefore, the stationary points are 2, 30 and 3, 29. Before tackling review exercise 3, let's recap some background. It is possible to find the constant of integration c when you have any point xy that the curve of the function passes through, or any value the function takes. In order to find c, integrate the function and substitute values xy of a point on the curve, or the value of a function at a given point, f of x equals k, into the integral function. Then solve the equation to find c. So let's apply this to review exercise 3. We have that the curve c passing through the point 4, 24 has equation y equals f of x. Given that f dash of x equals x cubed plus 3 all over root x, find the equation of c. So let's solve this. Let's rewrite f dash of x in a form we can integrate. So x cubed over root x becomes x to the power 5 over 2, and 3 over root x becomes 3x to the power minus a half. Therefore, given that these are the rules for integration, and in particular, for example, if dy dx equals kx to the power n, then y equals k over n plus 1 times x to the power n plus 1 plus c, where of course c is a constant and n does not equal minus 1. Applying this, we have this expression here for f of x. So x to the 5 over 2 integrated becomes x to the 5 over 2 plus 1, all over 5 over 2 plus 1. And similarly for the second term. And tidying up gives us this expression here. So f of x equals 2/5 x to the 5 over 2 plus 6x to the power half plus c. However, we know that f of 4 equals 24. And so, plugging in x equals 4 into this equation for f of x, we have this expression. And tidying up and rearranging gives us that c equals minus 0.8. Therefore, f of x equals 2/5 x to the 5 over 2 plus 6x to the power half minus 0.8. For review exercise 4, let's recap the area under a curve. The area between a positive curve, the x-axis, and the lines x equals a and x equals b is area equals integral between the limits a and b of y dx, where y equals f of x is the equation of the curve. A sketch will illustrate this. So we have the curve, we have the lines x equals a, x equals b, and we have the x-axis. And the shaded area is the area we're looking for. Let's now take a look at review exercise 4. Find the area of the region bounded by the line y equals 21 minus 3x and the curve with equation y equals 21 plus 4x minus x squared. So let's solve this. We're going to begin by sketching the curves on the same graph. Notice that y equals the quadratic can be factorized to 7 minus x times x plus 3. This of course makes it much easier to plot. Here we have the points of intersection with the x and y axes. And here's the line y equals 21 minus 3x. And the region we're looking for is this shaded region here in yellow. This is equal to the area under the quadratic minus the area under the straight line. We're going to call these areas Area 1 and Area 2 respectively. Area 1 is equal to the integral between the limits 0 and 7 of 21 plus 4x minus x squared dx. And integrating this gives us 21x plus 2x squared minus x cubed over 3. And of course, we're going to look between the limits 7 and 0. So calculating this gives us this integrated expression with x equals 7 substituted in, minus this integrated expression with x equals 0 substituted in. And calculating this gives us 130 and 2/3. So this is area 1. And now for area 2. This time we're integrating again between 0 and 7, but this time we're integrating the expression 21 minus 3x dx, as shown here. So 21 integrates to 21x, Minus 3x integrates to minus 3 over 2x squared. And plugging in x equals 7 into the integrated expression, and then taking away the integrated expression with x equals 0 substituted in, gives us 73.5. Of course, area equals area 1 minus area 2. So plugging in area 1 gives us 130 2/3. Plugging in area 2 gives us 73.5. And then carrying out the calculation gives us 57 1/6. This brings us to the end of this session. If you have understood its contents, you should be able to explore examples of differentiating functions with 2 or more terms, find the stationary points of a polynomial, find f of x given f dash of x and a point on the curve, and find the area bounded by curves and straight lines. Thank you very much for listening.